So let's start with, let's see. Okay, hold on here. All right. So this one, I think we have this one in our flow, right? So let's by this class, by this time, I guess you guys now get to like be familiar with the flow, right? Starting from the spec, and then you will get into the system design, which is like we have the architecture, and then we can do logic design. The logic design which has the ITL design, and then do the logic synthesis, and logic synthesis get out with the netlist. Then we do the test design. But the test design here, as the last time I said, the test design is a DFT, and DFT that's in the middle of the layout instead of like before going to the layout. Before going to the layout, DFT, that one is quite like a long time ago, but now it need to be like buried in the layout design, which is in the place and route. And after, let's say like let's assume that after this one done, we go to the layout design. What is the layout design? That's all say in here. We have a chip design planning. So we will talk about the detail today about like what is chip design planning, and then this one is in like a sequence, the step in sequence, right? So we have this one chip design planning, and then we have the bump part I/O integration, which is a design of the bump part and the I/O. This portion is about like the interface, and this portion is a PNR, place and routing. They call it place and routing, but the step that's missed from here is the CTS. The crucial step was missed here. It's crucial because that CTS step will design will design mostly. It's not design like it will design like the success of the PNR. If we have a good cloud, it means that like more than 50% our design will be successful. Sure, it need to be good in placement, need to be good in routing, it need to be good in CTS, all of them. But the CTS is very crucial because you see that the CTS is the reference of everything, right? It's the cloud, so it's the reference. If the reference is bogus, nothing works. The reference work, that means that the CTS is good, placement is not good, route is not good, it still works somehow. But if the CTS screw up, then nothing's working, which is like, we'll talk about that later. So after we have a layout, after we're done with that, we have the routed design. Then we get into the post layout verification, which is we have to do the logic verification again, because during the anytime, okay, let me remind you that anytime we change the netlist, like during the layout design, which is a place and route, the tool will insert the buffer or like a sizing or insert the buffer or change thing, so that it will like fix the setup, it will fix the whole timing, it will fix the timing actually. So anything happen like that, then we need to do the logic verification, because we never know if like those things like screw up our design. The second is timing verification, which is to verify if our design meet the timing, meet the performance. And physical verification, this one is to make sure there will be like a physical, which is on the layout, right? So we have to make sure that like this layout reflect or like really the implementation of the schematic we have, or like implementation of the RTL we have. So the RTL will be like synthesized into the gate netlist. The gate netlist will be implemented on the silicon, right? So they will be like on the layout. The layout then will be like will be made into mask and sent to the foundry to make like the chip. So the layout, so there will be like the verification. You see that layout versus schematic, which is like this one will convert the layout into like a schematic and then like compare that with the netlist. So that's it's that sort of verification too, but physical verification. Physical verification basically is this one. Yeah, I think this like is the whole thing like color color what dark green here. So first of all, the design rule check, as I talk about, like the Y need to be like having the need to have a minimum width, at least that width, and is distance from the distance between them, at least the mean spacing. That's the minimum rule from the very beginning. Later on, there will be the rule for the via. The via means like between, you see, between the middle, right? Middle 2 and middle 3, it need to be connected. Then that connection is realized by the via. So between middle 1 and middle 2, that's the via 1. So the via number is always taken after the lower layers. Middle 2 to middle 1 is a via 1. Middle 5 to middle 6 is a via 6. That's kind of like a convention, right? So the convention is so that you can see that. So in the interconnect system, there's only two type of thing. One is the middle layers, middle 1, 2, 3, 4 until like middle 10, the top layer. And then you have via 0, which is, I think that one is between like poly and middle 1. So poly is the transistor, right? The transistor is made by you have the poly in the middle of the two mode, right? Two diffusion area, N or P. So that poly will be like will be the gate of the MOS transistor. So that poly will be connected to the middle one. So that via will be called like a via 0, or it will be called something like, I think something, it depends on the vendor, the foundry. So from that middle 1 to middle 2, it will be via 1 and up until middle 9, 10, then via 9, and so on. The next one is like it will check the figure of verification, will check the EM and RD drop. This one IR drop. Actually, this one's okay. This one is IR drop. IR drop means you have a current and resistance. So you have a voltage equal to like current multiplied by resistance, right? So they call IR drop is when you have the source when it go into the cell, like the source is here, and go to the cell. Here's the cell, right? So go to the cell, so you have the current go through here, I here, and you have an R here. So when here you have a VDD, then at the cell, at the pin connect to the cell, you have, because the resistance from here to here, right? From here to here is a R. So the voltage drop in here is a IR. So that's what they call like IR drop. So they will check the IR drop to make sure that like the IR drop here cannot be like too much. Usually only like they allow about like 2-3%. So to make it happen, they have to have a very dense or very good power grid. The power grid usually is like when you hear the name like a grid, it means like this. So the power grid is like this. So you have that in almost every layers from the top layer down to, so that it will like provide the power, the VDD here, right? It's provide here. So to make sure that the current go through like those because when you have metal, that means you have a resistance. When you have resistance, the current go through that, then you have the drop, the voltage drop. The voltage drop need to be within like a 5% maximum, and in some like a high performance, they cannot allow like less than 3%. It depends, but basically 5%. So to make it, then they have to make, if you have a 1, right, 1 Y like that, 2 Y, that means R divided by 2, right? 10 Y divided by 10. And then if you have the width is double, so the resistance is divided by 2 too, and so on. So which is like the purpose is to make the IR drop minimum. All right. So that's about then you have the ESD is electrostatic discharge. This design usually You remember when you have we have the lining, right? So we have the lining or the high voltage. Our body is like a source of static electric static. So it's a lot of static charge on our body when we hold and chip. So that charge will like discharge into the pin of the IC. So you see that like there's so the chip need to be protected against the ESD. So they have the ESD. They have also the ESD device. It will be like a clamp, so that they put that into like they put that in the chip so that it provide like the protection, like it's some sort like the Zener diode, right? Diode. The Zener diode, when you have like a spike in the voltage, it will be clamped at a certain like a voltage, let's say like 0.7 or like a 1 volt or whatever. That's the some number. It depends on that you put 2, then it will be like a 1.4, or like you can like define that. So dosing is like the physical verification dosing. This will like allow us to make like the circuit. I think the DRC is a verification. LVS is a verification. Oh yeah, I missed this one. EM is an electro migration check. So this one is a check, verification check, because it's in the sense that like we have to okay, to protect against the they will calculate like that. They will calculate like the electron migration. They will calculate so that if we have a width, right, the middle width, the y width need to be larger than a certain number to make sure that like over time when we have electron migration and width, and then with they will limit the current, because the current need to be limited so that like it won't like inject or not reject the the electron from the Y, right? So you remember like when we have this, right, the Y like that, because the electron go out, right? So it go out like not evenly, so not everything go now. So at something like as defect, this one will go out more than in this one. And after a certain time, this one become like a critical, or like even become like a open, so the circuit won't work anymore. So the EM, the way it works here is the EM, it will calculate the current through here, calculate the E here, and they calculate the width here. So with this width, that means like with this width, they will like allow only a certain like a max, I max, I average, actually I average max, right? So that like over, let's say like the life of 10 years or 20 years, this one is still like even with the electron migration, is still okay to like conduct well. If let's say like the limit here is like it allow only like a 10 milliamp, right? But we just like put it like to 20 milliamp, then it will like the IM, the EM will like accelerate and then will die, like it will cut this off like before the 10 years limitation. All right, so that's like just talk briefly about each step. Now we go to like each step. I think this one is just repeat, right? I think it's okay. The first thing is design spec. Design spec is, I think, what is specified here, like it uses which technology. So you use a which technology, 45, 28. Okay, it means that this okay. Or like nowadays is 4 nanometer, but for the analog is still in the range of, I think analog is still in the technology of like a 40 nanometer or 28. I think about that. But the digital is you have two things for the digital and analog. Analog like you have the amplifier, you have the op amp, right? You have it all like ADDA and the filter, whatever is not digital, that's the analog signal. Digital, we know that it's like the N or whatever. So the digital currently like go to the 3 nanometer, but this one is still stuck at I think the 40 nanometer. or like 28. The reason why, let's say an antenna or like things like analog like L or C, right? L or C, that means this one is to make like the resonance, the inductance, like the resonant return. Those things cannot be scaled like minimized because the L, like the inductance and capacitance, they are proportional to the size. And because of it, those LC is like even we have our cell, our like cell is very small, but those element is very big. You see that it's in the ball. We have the chemical capacitance, right, in the ball, and that ball like that capacitance is still like big versus the chip, right? The chip's getting smaller, but those analog never, because it doesn't get smaller, so it's no point to get to like a 3 or 4 nanometer technology. So they still like at the 40 or 28. That's the reason why. So they will, because you have a 40 to 28. That's really a very big advancement in the analog design, because I think 20 years ago is in the range of like maybe, let me see, in the micron thing, like a 1 or 2 micron thing. 20 years ago, the digital is at about half micron or like a 100 micron. Yeah, 100 micron. Sorry, 100 nanometer. But now it's like you go from 100 to 3 nanometer. It's just like they have a joke that they said that you see that the chip evolved, right, from like let's say like a couple thousand transistor in the first processor. Like the first processor is a 4004, couple thousand transistor. Now it's a 16 billion transistor. So which is, I said that like if, and then the price even go down, right? At the time, the chip is even couple thousand transistor. It costed in the $100s or even $1,000. And nowadays we have like 100 with more than that, and they make a joke that like if the automobile industry, if they can scale like the chip, I think we have the car right now. It just costs maybe like in the dollars, not the $20,000. So, but that's a joke because I think the car is different. Now it's okay. What is a cell? The cell is a macro or functional unit that performs common operations and is used to build more complex logic blocks. It's always, I think it's very clear. I don't need to add anything here. So the standard cells like inverter, NAND, NOR, and so on, right? Then you have a standard cell. Standard cell means like a very simple, the building block, which is inverter, NAND, NOR, flop, latch, and buffer. That's the minimum. However, there will be like along the way, they just put like the standard cell, they put it more like you have a AO, like AND OR inverter, AND OR, which is like a complicated, complex cell, but it's still standard cell. Like we can have that in this list. We have AOI, AO or AOI, or OAI, OA, OAI, right? AO like AND and OR, right? So OA, whatever, and I at the end means like inverter at the end. And then they have a multiplexer, the MUX, and they have you have the MUX, you have like an adder will belong to the macro cell, but yeah, it would belong to the macro cell. You have the MUX and have a couple more things here. I think half adder or 10. Macro cells. Macro cell is like complicated cell with all the kind of like it's done, but with complex function to be simple. Like you have whatever, like a POL, you have actually those in the macro cell. Okay, to put it simple, macro cell is a functional unit. more complicated than the cell. So what is IP? IP is just a macro cell, but like you have to buy it because it's done by a certain like a vendor, third vendor. So because they made it with a certain like performance or something, and let's say like they make a very good multiplier very fast, then they just wrap it into like a black box, and they just sell it, and we take it, we put in our when we have to buy it because it's IP, intellectual property, right? We have to buy it. The macro cells, the macro cell that we have to buy, that's IP. What is a cell library? So cell library means like it's a library of all the building block. So the building block will have like I think the standard cell, right? Okay, the two things, analog. Like we have the POL is the analog, ADDA is a block, is analog. So USB is also an analog, actually mixed signal between analog and digital. So those things, so that because whatever in our design need, the library will provide the building block so that we can make our design. Let's say that our design like that, we need the POL right here, so that it's provide the clock, right? We need the memory. We put that here. So we need those memory come from the library. And then we have like the IO cell. This one is a chip, right? This one is an IC. So it need to have the IO cell here to like connect to the output. So I need the IO cell and so on. So that means like the cell library is a library of all building block, so that to allow us to implement our design. So that means it has an IO cell. You have this they list this thing is the basic block. There will be like some other thing depends on like the design. Let's say like if the RF design, they have the antenna, they have the RF components. For like digital, we don't deal with that because of the analog. The analog we deal with in our digital design is basically is the POL, because the POL here we provide from the POL it will provide the clock. We need the clock, so we need the POL, and then that POL will make the clock for us, generate the clock for us. The cell library, I think in terms of like the format, there will be like I think three. Yeah, I think that's like a three time of format. Depends on like the stage in the flow, the design flow. So I think maybe it's this one. Yeah, the first one is a schematic, right? Schematic is just like uh, okay. I think we go to the next one to see like what schematic what it is, but the schematic so that like you have the description of like description of the circuit, but it's easier to look into the schematic to see like how the circuits work, right? And then we can like probe, or we can like see the flow of signal. So schematic is for the practicality is useful when we debug, because we cannot see the schematic of the whole design of like a billion transistor for sure, but we can look at like for a critical part, the part of like 20 stages, or like something we want to see if like okay, our part doesn't meet the timing requirement, so we need to see why it doesn't, what is the problem, and what's the sound there, what's whatever. So if we look at the schematic, it's easier to see how it flows. And also I think the schematic is when we want to yeah, for debug, the schematic is good to like have a visual image of the circuit. The front-end model is a Verilog, those kind of thing that you know already. So the Verilog, the netlist, that's the front-end model. The back-end model, we have a left. Okay. The most used is the left. It's another one, depth. Is that here? No, it's not. So left, depth, and GDS. GDS, we don't see that. This one is to like go to the foundry. So I think, okay, we go to detail later. So that means that we have here we have left and depth and GDS. So what is those things? So Verilog, you know, this portion you know it already, right? So no need to explain. The library.lib, this one is the format of synopsis that everybody now use. So in this, it will describe like we have a lot of information here. It will like give us information about the delay, about the transition time, about the leakage, and about the switching power, like a power switching SW. So leakage. So that's basic delay, transition, linkage. Yeah, those things. So that means that the you can see that, and then they have some like max cap, a DRV, which is you have design. I think I use so much now I don't remember what it is. This one is to check 310. Okay, let me. This one will give you three. It will give us like three types of max fan out, max capacitance, and I think there's also okay. This is the two things: max fan out, max capacitance, and max transition. But here, max transition here. So what is it about? First of all, delay. So you have the table. For the delay, you have the table. Remember, I think I explained to you this. Here's the load, and here's the input transition. Then for each load and each in transition, you have a delay here, D1, and this, you have a delay go like this. That's the table of delay. Now for the table of max transition, the same thing. Depending on the load and the input transition, you have the output transition will be here. So you have the same table. It will be like that too. Load, input transition, and you have an output transition here. So that means like if you apply, for the cell, let's say you have this, you have the cell simple like inverter. If you apply this one, you have a load. Let's say you have a two inverter at the output. So the load here will be some like equivalent this one to a certain C load, right? C load. So you apply a certain like input transition here, then the library, the dot lib here will give you the data about the delay from here to here, right? Delay from here to here. Because you have an input transition here, you have a C load here, that's the two things. Input transition and load here. Then you got the delay from like A here to B. At the same time, with the same information, it will give you the output transition here. So you got the output transition here. So that this one you will apply to the next stage. And so on, you just like apply that like a forward to have the delay of the circuit. That is about delay and transition. Then there's the limit. Why do we have the max fan out and max capacitance here? Max fan out because the max fan out because that's a high fan out. When you have the max fan out here is going along with the max capacitance. So max capacitance, why? Because the max capacitance, because this. When you have the capacitance, the load, capacitance means like max capacitance, it means a max load. Load is a capacitance. So the load, the input transition load table here, it has the load L1 until Ln, right? So the maximum here, it has a certain like range. Let's say it go from here into like 1 picofarad. 1 picofarad. So which is here they will put like the max capacitance here might be 2 picofarad. I make up number, it's not real. But why it's not like the 1 picofarad but 2 picofarad? It depends on like how comfortable they, when they characterize this table, they have this table. They see that because when this, when we have the load is bigger than outside of the table, it's outside here, right? So it cannot find the value. So how do they do that? They will do a process, it's called extrapolation. Uh, extrapolation, interpolation and extrapolation, which is like this. Let me, okay. I know that if I write here, it will be confusing, but I will delete that. Okay, so but because I don't, if I switch into the whiteboard, it will be complicated and will miss it. So I just put in like easy like this. Here, let's say we have this one is a load here, right? With the same input transition, you have the delay out here. So that means that it will be like this. It's with input transition, it will be like this, right? So this usually it go like this. This one is the range, like the maximum, that's a 1 picofarad here. Now you have a 2 picofarad is out. So the way, let's say it's like 1 picofarad, if the load is 1.2, it's right here, right? 1.2 here, then it will extrapolate, just linearize. They just take the 2 points like this and linearize. Just extend that, but linearize. You know what linearize is, right? So let's say like the first one here, the 2 points in the table is like this. They just like extrapolate. That means extend that linearly, and you have this one. When the thing is go out like further away like this here, like the points here, right? They keep like extrapolate until like that. That's wrong, because you see that the shape here is not like a linear. It's kind of like exponential. So like when it's here, it's supposed to be like this, right? It's up over here. But if we extrapolate linearly, we get the number here, which is very wrong. That's why it will have to put a number maximum like, oh, I have it here. I put like maybe 20% above the range in the table. So if the table is 1 picofarad, the max gap will be about 1.2 picofarad, something like that. Right? The same thing for the input transition. So there will be like you have a max transition. You cannot put like more than that. If the transition in the table is 1 nanosecond, you cannot like input. You cannot have the transition at 2 nanoseconds because the data will be wrong. All right. Let me remind you guys one more time. If you have a question, you write it in the message board, and then speak up so that I pay attention to that, because I look into the slides right now and I explain on that, so I didn't pay attention to the message board. So I need some like some voice to remind me that. Okay. So okay, let's say now it's with that. Let me remove it. Let me clean it up so that like I think that's there won't be like a complaint that it's confusing. Right. Okay, now the third format is the left. What is the left? You can see that from the left here, two things important, which is like it gives you the physical shape of the cell. The left will present like a physical representation of the cell. So that means you need to have the size, and with the size here, it will have also the size x and y. I think there's always x and y symmetry and yx. Yeah, here you have size x and y, right? So symmetry y next, and then it will have the pin location, and describe that. You see that it will be like this pin A will be on layer M1, and you have this one, the rectangle, this one, and then location and this one at this location. The same thing, pin B like that. So if you look at like here, this one is like the left. So it describes like the pin B and pin A location, and then the size, right? The size like you have the width and the width here and the height. The second one is this one is the detail layout. This one detail layout. This is the detail layout of the inverter. Usually, this one will be like buried down in the hierarchy. Usually, it won't show unless you want to click on that and you want to like really look into detail. So by default, it won't show you because it will be crowded, right? In the layout, there's too much thin already. So for the cell, they want to see only here because the thin inside. Usually, nobody cares. Only when they check DSC, there's something that they want to look at that, but nobody really cares what is inside the cell. They only care about this, so that like, oh, here is connect to something, here is connect to something, and they go from there. So this one is a detail layout. It's only when we have some bug or some like some error happen for the design room. Let's say like this one like this. If the let's say like you have this one, right? This one is the y here, and we put the y outside here. We put like next to that. So it's too close. It causes like the design like error, design rule error, which is a DRC error. When we see like because the thing inside here, we don't know that. But here's our y here. We just see, oh, suddenly we have our y here has a problem. Then we need to look into a side. But usually we really don't care about the inside. This one is just like to explain like what it is. And on the right, you see the schematic. The schematic of this one. The schematic of this one is the level of the level transistor, right? Because you have transistor here. You have transistor here and transistor here, right? That, but when you have this one is then up a level, there will be like schematic of like only the cell, and you have up another level, you have like the schematic of only like the level, one more level, and so on. That will be hierarchy, and we can look at that. And the dev file is described. Dev file is a design something. The dev file, I think it doesn't talk here. It doesn't mention here. But this one is to describe the location or like the shape, the Y, right? So when you have like you have the middle Y connected between the cell, those connected Y will be described in this depth. The left file is for the left file is to describe the shape of a cell. This one for the cell, but the depth is for the design, not for the cell. So this depth will like describe the connection, the Y connection. Layout methodology. Okay, all those kind of things, I think what we focus on is this one. This one is what we are doing. And this one too. So the get array method, I think is not, we are not working on that, so just ignore it. And these two things, yeah, this individual design method is we do with the analog that we don't do, right? So that means like we just do like cell-based method, PNR, place and route, and like hierarchical cell-based method. So this one will be to build a block, right? To be simple, and you can imagine that quickly. This one is a top-down, which is we have when we design top-down, but when we like implement that, we implement like a bottom-up. So first of all, we have our design like that. We partition that into this block, and this block. and in each block like that, it can be like a smaller block, right? And so on, and so you go. So that's like a hierarchical, but you cannot build like a from up from like the top down, right? Here, so you like have the design like a planning, you design top down, but now you implement that, you have to implement like a this one is a building block. Let's say like the same thing as a unit, the building block as the cell library. From cell library, you build like a smaller block. Many smaller block will make a bigger block, and then like it make like many block will make to the chip. So that's like that's the number 4. Number 3 and number 4 is not excluded. It's like the number 4. The number 4 is using the number 3, because this one is not like, oh, you have the cell-based method. It's not the same as the hierarchical cell-based method. Yeah, it's a say like cell-based method too, but like do that hierarchical. So these two things is, this one is when we do like this one, that means it has our one block, and there's no like hierarchy is no hierarchy in the design. This one, let's say if you design block, it's just like that, and you have really like only cell in there. There's nothing else. That's a simple cell-based method. But in real life, that's this one. So let's go to like what is the standard cell structure of the cell-based method? What is a cell-based method first? The cell-based method, I think it was explained before that. Let me see. I think it's this one. You see, here's the design. Let's say the design, right? So it has like a built-in like a it had built-in row here. So the row here will be defined like predetermined. You have the predetermined row here. So the chip will be like divided, and then have the row determined like this, and then each row high is the cell high. That's why it's called a cell base. Each row high is like this. The row that you see here, right? This one is like that, is a one row. It's like that, one row. And one row like that, you can see that the cell is a fit into one row, and the cell high is the row high at the same time. So you go back to that. So this one is one row like that. If you extend this one, it will be one row. So the basic concept of the cell-based method is they will, because it has it, so that means like go back here. So you have the VDD usually at the top and the bottom of the cell row, and they will do like this. If you have this, right? So let's say I just like illustrate at a demo like this. Let's say this one is a one row, right? This one is one row. That's what we talk about here. Then this one will be VDD. This one VSS. And then it will like a repeat VDD and VSS. It means that if your cell is like here, right? It's like let's say like here. One here, the input and output here. Then the next row here, it will be flipped over to have this, and it will become like this. Is that I think it's confusing. Let me draw that bigger. So 1, 2, 3. If a cell like this one will have VDD, VSS, and VDD. So a cell like that, you have the same cell, right? The same cell is A input here and B output here. So if the cell is placed this way, in the next row it will be placed, but it will be like a flip, so that you have here is input and here's the output. See that? So this which means you have the way it placed like that. You see that it's not like the same cell is placed the same like orientation. That's what it called. So orientation here, you hit it, let's say like orientation is the F, they call that F. The other one will be F0, so this one will be like this, right? Go this way, and this one go like this way. So even like it say like that, but actually the look the one is a place the cell here is not simple like you just put the cell the same orientation, same direction. If the same cell put in this location, it will be like let's say like up north. So this one when you put in the next row, it will be like down south, go south, and so on. That's like up, like up or down. So the cell base mean that way. So it define the cell row, and all the cell will have the same like a definition, like it need to have the cell height the same. All the cell need to have the same cell height or multiple height. So that because the multiple, it means it can put like that, right? And it can get like you have a here, but even multiple row, it will have like a VDD here. It will be inside, it will VDD here, it will have a VSS here and VDD here. So that means even that you don't have a VDD up here and VSS down here, because when you plug into the design, this one need to be VDD. So every row there will be like a VAD and VSS alternatively. So in that, beside that, you have the signal port. The signal port need to be like you have the track, the routing track. The routing track, which means like those things will be like the wire will go along like this. It doesn't go like it doesn't the wiring doesn't go any chaotically. It need to follow the track defined here, right? So if you have this, you have the row like this, so it will define the track like this. You will define the track, and then the wire need to be placed on this track. And because the wire need to place on this track, so the signal port need to be on the track, so that like it just right, like the route go to the port and it connect directly. Because if we have the signal port is not on the track, right? Let's say that in the middle here, then the wire you go to here to get to the signal port to connect to that, it will need to like add the extra metal to go to that. It will be confusing and will be messy. So to make it easier, they put like the signal port on the track, which they call it wiring grid or like the track TRACK. All right, so with that, yeah, that's why I call like on grid. So the width, okay, by the way, the height is fixed to the cell height, right, or multiple cell height, but the width it will be like multiple of the wiring grid. So but the wiring grid or like the wiring track. So let's say like you have this one here is the wiring grid. So if the wiring grid here this way, and then that means that the cell width will be multiple of that wiring grid. And wiring grid, the Y2 is will be like you have the height will be multiple of the wiring grid of the Y-axis too. Okay. This picture explains quite like basically what the design or the chip is, right? So we have I think this is a bonding part. The bonding part here is to connect to like outside. The I/O cell here is placed around, so that like from here it will like be connected to the bonding part. The bonding part is that's what you see like outside of the chip, right? The middle outside of the chip, that's the bonding part. Actually, it's not really that bonding part. This one is connected to the that what we see. It's not that. It's not yet to be like okay. Let me clarify this. First of all, the IO cell. The IO cell in this one, it will, because this why we need the IO cell here. Why don't we, like we have the cell here is right all the way out to the external world. We need the IO cell is the middleman to have, because the cell in here, right? The cell in here is driving between them. It's a very small cell, very small capacitance, parasitic, and like a very like a low resistance and so on. All the load in here very small. But when you get into outside here, now it will connect to the PCB, right? This one will go to the PCB. Let's say you have another chip here. So you go from this to this. So which is this one? You remember inside here, it will be like the size of like the distance between the cell will be like only like a micron, or like yeah, only micron. But when you get into when the chip go to another chip, the PCB, this one, the distance between them will be like the centimeter, right? Centimeter, and the size here, the Y here, so it can be like in the millimeter. Versus inside here, right? Inside here, it will be like a nanometer, or like a micron. You see that? So which is whatever the cells inside this driving, if it has to drive outside here, it will be dead because the load is too much. The load inside here, will be in the femtofarad. But when you go out here, the load will be picofarad. So you need a bigger guy stay in the middle to like a buffer, right? A buffer to be able to like drive the outside world. That's the first thing. The second thing is like because this one, it need to have some protection for the circuit inside, which is the IO here will have the mechanism to protect the internal circuit here. So whatever go out in here is go to the IO. In the IO will have the ESD port, will have the protection and so on. So that like the outside world cannot hurt the internal like a chip here. So internal serial, you have this IP, right? IP model area, it doesn't need to be in the corner like that. It can be like all over, but usually it won't be in the middle. It will be placed around the corner, around the edge. The reason why we will see that in the placement. And AI, I don't know what that means, AI here. The wiring can run in free channel and through over cells. So you see that this one, the cell is here, is the bottom, right? The middle layers will be on top of it. So that means the middle layer, the wire will be run all over the chip, on top of the cell. Because the cell usually use like up to like usually the standard cell use only middle 1 or like middle 2. The bigger cell will use to the middle 3. So when we have it, usually I think it will be opened up so that like because, for example here, let me go back to this one. You see that this cell, right, is in symbol 1, use this one. This one is the poly that I talk about. And this one is a middle one, for example. Middle one is connected between like the P transistor here and the N transistor here. It connects here, right? So you see that is the connection in the middle here. This one is the middle one. But you see that middle one used from here to here only. So that means that all the thing left here is kind of empty. So the routing rule can use the empty here to like insert the middle one here, which is like the cell. Usually I think the standard cell they will be seen by the tool that up down to the like the middle one, so that they can know like, oh, I see that like has nothing here, so they will route the even to middle one. All right. So they said that like wiring can run in free channel and through over cells. I think you take it as like the wiring can run all over the cells, and it can go like it can go into the cells in the empty space if it is allowed. There's a cell that they sell like the multiplier because of the high performance. Even there will be empty space in there, but they don't want anybody to go in there because they will, when we route inside, it will like have the crosstalk, it will have the coupling capacitance, so they don't allow us to use the space inside the cell. So usually is the over the cell, that's the most common. Hierarchical, that's what we talk about, right? So the same thing, you see that this one is just move like, now you have a 2 block, and inside this block, I think they can have like another level. Our design is to have about like 4 level. So we have the top level, and you have a DL1, DL2, and DL3. So it depends upon the complexity of the design that you have like a design level 1, 2, 3, 4 hierarchical. Imagine that like it's all depends on the complexity and also the size. The size, because the currently the SDA tool, they run the timing for like, imagine that if it has to run the timing for that is 16 billion transistor, no tool can do it, right? So they have to divide and conquer. So which is they have to divide that into blocks so that they do that on like each block. So then they will do the timing for each block, and then divide, if still like a big, right, 16 billion, so you divide it down, you still have, let's say 16 block, you still have 1 billion, still too much. That's why I think we have to go to like the level like 4. And when you go to level 4, you have like about couple like 20 30 million transistor. Then I think the current tool can do the SDA, can do the place and route and so on. Because more than that, imagine that like if you do that for 100 million transistor, do the timing, do the place and route, the placement, and do the routing. Let's say the routing, it will take like days to do that. Imagine that only 100 million transistor to take day to do that, and then now you put in like a 1 billion transistor, it will run forever, because the complexity is not linearly proportional. It will be exponential. So that's why I think no tool, no EDA tool right now can offer, they can like handle like more than, let's say, like a half billion transistor. They can. So that's why the hierarchical cell-based method, or hierarchical like a method, still cell-based. By the way, you can see that the row between here is not the same. Why? Because the way that we define the row here, that's by the tool. On the silicon, there's no such row, right? On the silicon, there's no such row. So that means the tool will define that so that it can handle, it can know like where the cells to place. But in the silicon, don't have it. Because of it, when we put it in, like the row in between is not like a line. But when we have that, it will have like they will have the connection between the two. It will try to align. So those pin, right? This one is this block and this block. They will be the input and output of each block. It's called interface. So go from this block to this block. So that means they will have to put the pin align on the grid of this chip. So now this chip will have some cell row by itself, which is this cell row here has nothing to do with cell row here and cell row here. But the pin here need to be aligned with this thing so that it can route correctly. All right, so we take a break now, and we go to this package. I have somebody have some question. Oh, there's only like 12 students today. All right. By the way, okay, I think I will send like there's a two. By the way, for the package, there will be something. Let me share this one. There's a two document very good for the package. I think you guys can read it. This one is just for read for fun and then understand right away. There's a nothing. Let me share this one. Yeah, this one is about the package 10. I think we will update it. So in the 2000, but it's still okay. So I think we don't need there's some more like advanced packaging, but we just got the idea, right? So in this one, it will talk about the package. So like this, the package parameters, what is needed, and then number of terminal, talk about the the thermal design consideration. Just read for the understanding, and it's not rocket science. It's just like you read and you understand, you have some idea about that. Reliability, testability. So it's just a that's the package. The package heatsink, this isolation, and then like they model the package substrate, a package in plastic, and then package ceramic. You see that the chip, whatever like wrapping the circuit inside, that's a package, right? Simple. So I think this one is the reference for you to read, and yeah. Okay, sorry. Take a break now, and we continue in 10 minutes. Okay. All right. Let's get back to the class. So one of the thing is, I think the first thing, I think we get through this one quickly because the package thing here is nothing. I think it's not really our thing to do, because later when we have those things will give you a hint, an idea about like what the package are. However, those things will be implemented by a separate facility, not by us. Even like Qualcomm, when they make the chip, you can see the SoC chip here, right? We make the chip here, but the package here will be done by another company. Actually, the chip here is done by TSMC, but even the package here is done like by another company. So there will be like design to that, but the fabrication will be done by the other company. So there's the package time we have. I think we talked about that a little bit earlier. Like SIP is system in package. You see that the package is you have this package with the bond here, right? With the bond pin here. So it is like you have the memory here, you have the chip here, SoC here, and it's connected. This in you have the system, and it will be like in the same package. They call it system in package. The difference between system in package and this one is that you have a SoC here. That means that SoC, the system on chip. So it's like you see these two things will be on the same chip. It's not like two different things, right? Here you see two things. The thing here, uh, you see, do you see my mouse move? Hold on. Okay. Này. Oh, now it's. Oh, okay. Let's see. Oh, it moves slowly. Okay. Thank you, Anne. Okay, you see that this one is I think you have a two thing here. That's why like you have a two chip here, and then put alongside like together the system in package. The system on chip is that these two memory and the thing here, it will be like together. So it's chip, and then this the whole chip is in the package. Uh, Here you have a three thing, right? You have the system on chip, whatever. I think this one memory. Yeah, I think this one is just another one. Stud bump. You have the thing inside here so that it connect outside. Now you have a package on package, which is you have a package inside package. That's all. And then package routing, you put it in, right? So you have the SoC chip. There will be the pin. So you see that the pin in the here, right? The pin here is in the SoC, and it will be routed outside to the solder board. Yeah, to this pin like a router to connect to the PCB. And the next one is the flip chip. Flip chip. Okay, I think that simple as flip chip as like when you have I think it will. I think read for this flip chip, read into the material I will send you later. It will explain this one too. It will explain that chip size and bumper planning. Those things I think is yeah. So you have the bump here. Those bump here to be in the middle will be the chip in the middle, and it will go into the bump, and then from the bump here it will be going outside. This one you have, yeah, I think it's okay. Usually those bump here, there's a two thing. The bumps here, there is two type of bump here. One is the power bump, and one is the signal bump. So the bump, so one is the power here to connect to the power inside. So the actually the chip can be like this. The bump here, oh, this is the flip chip. So the flip chip, so all the bumps is over the chip. For the okay, let me show you. Yeah, here is the Y bond, but it's this here is some confusion here. Um, okay, to be simple, you got some idea about the flip chip, and then from the package in here, right? So this thing is like even show that, but I think we need to see like the real thing. This one, yeah, you read. I think read in the material, there will be like a clearer definition and clearer explanation. This thing. So I want to go to the next one. Um, okay, I think this one, maybe this one. The bump assignment and block placement and power arrangement. That's the good one. So you have the bump all over, right? The bump all over. But in that, all the bumps are not equal. There will be bump to be assigned to be power. Yeah, assignment. So right, power area and the position. So there will be, you see it, power shut off area. So you have that. It will be like there's a bump assigned to this. There's a bump assigned to the other one, and the bump around the bump here, there will be assignment for like a signal and the power thing. Yeah, I think it's in this chip. Is this SoC? You have the PCI USB 3 here. It's a connection here, and then you have I/O for 1.8 volt here, and you have a DDR. DDR is like to interface with the outside. For this one, I think I have analog here, analog block here, analog HM here, and so on. Well, okay, this one is another one to like they have to analyze the IR drop. You see that this thing is the IR drop, like IR drop thing. When it's red like that, it means like here you have they will consume a lot of power, so that means red because it consume a lot of power, which means we have like a higher or a bigger IR drop. To avoid that, then that means like we need to provide more bump in here so that like the current can be provided to this area more than the other one, right? So here is like a green or a distance. Distance is almost it doesn't consume, it consume very least power. So the number of bond of things at the side here will be less. This one will be more. I think that's why I think they make like a more bump here. They contribute now you can see that, right? You can see that it's make more bump here to provide more power, but the other one not. It depends on the power analysis. Okay, now we have we go to the biggest and the most important of the layout design that we can have a chance to do that in the next when like I think according to Professor Ten and like the discussion with Renaissance and Cadence, if we have a chance to get the PNR tool like Innovus from Cadence, then I think you guys can like explore this. This is very like critical. So this one you can see that initially, okay, the flow of the PNR. First of all, it need to have the I/O placement. So these two will be like I/O placement and floor planning, right? This one is usually this portion is a floor planning. What is a floor planning? You remember it's how to place the macro. Usually you have macro, then you floor planning. Okay, floor planning is floor planning is a process that you will define the shape, the size of each block. And the floor planning, there's a two level. At the top level, like this. Let's say at the top level. So let's say you have two blocks, and then you can define like this block have this shape, the other one have this shape, and the other one have this shape. That's the floor planning of the top level. Now at the block level, let's say for this one, Now they have to the block level it will define. In this, let's say I have memory, so the floor planning will involve to where to place those memory. Put it here, or put it here, or put it here, and so on. So that means that those things like the placement of the macro usually is done by hand, is done manually, and then it will be like a trial error. Until now, there's not really a tool or software to be able to do the automatic placement of the macro. There's none until now. People like there's a lot of research on like doing like a macro placement, but nothing's working because it depends on a lot of the timing critical, especially the timing, and also like it evolved into like it need to after you place it, you have to run placement, and then you have to go down the row until like the routing to see like what is the timing. So the cycle, you see the cycle from here until here, it takes about like it takes about if everything is correct, it takes about like 1 week at least. But when we have from the beginning, when the timing is bogus, when we have thing here and there, when let's say like when you have the timing is not met, right? Let's say you target to like 2 gigahertz, but your design you run that because first time you don't know where you should play the macro, you don't know like how to optimize it and where to optimize, then you just reach 1 gigahertz. Because you reach only 1 gigahertz, so the tool try very hard to optimize it. The more because it has, if let's say like if your design like reach 2 gigahertz, then it run quick, right? But because now it only 1 gigahertz, and you want that to reach, you want that to perform at 2 gigahertz, then the tool need to like work harder or need to optimize a lot. So because of it, at the beginning, if you got like 1 gigahertz, you get to 2 gigahertz, it will run like not 1 week, it can run like for months. So which is that's why the critical phase is a floor planning. You need to like the there's no such like a macro placement like automatic that. I think if somebody can come up with that, that will be like a billion, like a million value 10 because the time one okay, some number for you to imagine the time to do the floor planning like a trial and error here. It took like a month, 1 or 2 months to like figure out what is the replacement, the decent placement. We cannot say like the best because when we try something new, maybe there's something better. We cannot prove that is the best. We have no way to prove that it's best. We just see that this one is the best in everything that we try, but we cannot say that it's best. So which means like this floor planning here is very critical. It's quite like a I think it go from here. It's like a loop like this. Is you do that, and then you have like you have to place and route, and you measure the timing. Analyze timing, and you go back. Okay, now we have, for example, let's say I think I make an example why it's a turnaround. Here's our chip. Let's say you put like one macro here and one macro here, right? One macro here, and then the logic it goes like and then out. Here's the IO. So the logic it go like up here and then go back here. Let's say for example like that. So when we put the thing like that, then we think that like we just okay. First of all, we put that we see that this one and this one, right? This thing and this thing is far away from the IO. We need to put it up here. That's after we got the feedback, we put it up here, right? We put it up here. But then there's a lot of like a lot of cell here. It talk to this, so it just go back here and go like that. It make it worse. So that we have to like put that somewhere here, for example. So which is the trial and error here is really we have to like we have the placement, then we run route and so on, and then we see that okay, this one, where's the critical part? The critical part, let's say like it's now. We put it here initially, and then we have output here. So we see the critical path go from here to here, so far away, right? Then after that, we see that the second floor plan we will move up here closer. We move closer. Then after we do that, we see like, oh, now the frequency, the critical path after this, like that. Now the critical path now become like it goes here, like this. Then we have to move this one like up down here. Then I think it's just like move thing like this. It's a shorter, right? So that's an example that like here we involve only two blocks. When we have a multiple block, it get even like you don't know how many like combination. For the example, in one design, I try like about like at least like about 50 to like 100 floor plan before I come to like the final floor plan. So each time we try like we don't try like one after the other. We try each time we try the five floor plan or like 5 or 10, and then we just analyze that and we pick the two and then we add some more. So like that, usually one design got about 50 to 100 floor plan to like before it settle down. That's why it take about like 1 or 2 months to settle down the floor plan. Then after floor plan, you have the power supply design. So when you put like right, the floor plan means like the definition of the shape here, right? This one is a negotiation with the other block owner. So they will negotiate, and they will negotiate what do they negotiate? The shape and the size. Let's say like when my block is like this, I want that like to be bigger because the bigger means I have more room to do and it's easier to design. But the other guy now, oh, you take that away from like my place, so you need to give me back. So that means that finally, okay, I give you back this corner, for example. So the shape will become like this, and so on. So that's one aspect of the floor plan. The next aspect of floor plan is that we will do the I/O, because the block need to be interfaced with the other block, right? So it interface through the input and output pin. So you put the input here, or you put that here, or you put that here, or here, or here, whatever. So how do we do that? Again, negotiation with the other block owner in the, let's say the big block like this. So that means like here I have a block here too. I have a block here too, block. Then if like whenever the usually I think whenever the signal talk to the other one, we put that close to that, right? So usually, but when you put that here, that means you see that the input, if it's like here, then it affect the way that we put the macro inside, right? Because the macro here, if you go here, then you have to move this one down. So that means that the first thing to do is that we have to negotiate first the IO, where the IO location are regarding the other block. After we define the IO, then we start to do after we define the IO and once we like agree in terms of the shape, then we start to do the floor plan, which is we start to do the macro placement. After everything like we have a shape, it's done, the IO location, and then you have the macro like placement, then you start to build the power supply. The power supply will mean like the power grid. You put the power grid, right? You put the power grid so that like it will provide the power to the voltage to the cell. After going there, so after that, this power supply, this one actually we call it, these three basically is a floor plan step. Then it's done. Then we have now we do the placement and route. So what do we do in the placement and route? It's the next one. Okay, we go ahead. This one's auto. Okay, size, shape, right? It's apply whole design cycle. Yeah, it has to go like its block is apply the whole design cycle. Interface model. You have interface negotiate that, and then like use. Okay, so that's like so again, I think this thing to come up with a floor plan. So actually I think this one is not, it's not very clear. So there's a three things for floor plan. First is shape, right, and size of that, and then IO placement. And the third is the macro placement. So that's a three, and then the fourth is a power grid. But at here it say like power grid is separate. But anyway, power grid. So and then after you do that, then now you do the power grid. Power grid for the simple block, there will be two in the vendor. The vendor, the tool like Innoverse, the place around will have the tool, the feature to route the power grid. So which is this one. It will give you that. And semi-automatic, this one is, I think this one is like some company do that for a special like a design, for the specific designs. So Renesas has it, Qualcomm has it, everybody has it, but they tend not to use it because when you do that, you have to have a team to maintain it, and then to like when it advanced, right? So have a team to maintain. They want to cut costs, so they just try to use the vendor tool. If anything they need, like more than like what currently offered by the tool, they will ask the vendor to like a cadence, ask, okay, I need this feature, I need this feature. The vendor will be happy to do that because that will give them the edge, the advantage that okay, our tool like can handle many feature like that the customer needs. And with that, they will like tie the customer to the tool because the customer has some specific demand, right? And then they request the vendor, which is like the cadence to do that. And cadence will do that so that they will hook the customer into their design, because they go somewhere they will have that like a thing from the customer like a Qualcomm or Renesas. They will have advantage that like they don't have to spend time and spend money on the team to do that for them, to do those specific. So the semi-automatic design, I think usually it work this way. Usually we did something like because our design like is specific, so we need some specific need. Because it's a specific, the tool cannot like satisfy our demand, so we have to like drive our code to do that. The problem with that is that we need to maintain, right? We need to support that. We have some code to like let's say we write some power grid with a specific like goal and like a uh, very good performance. However, we do that, it need to be applied to every design in the company. So we need to support the company, but we are not the support. We do that for our design only. Now, if that one is good, and then the company like the other design team want to use that too, either like we have to support that for them, because when they use that, there will be bug, there will be like they still have their own like request, their own like specific request, which is we have to support them. So from that point of view, like even we have a very specific like a good idea or something like a patent, but we cannot patent it because we have to give that to the vendor so that they take that idea, they implement that. Once they ever implement that, they will support the whole company. Then they will support the whole company, and they will support like then from the point of view of the customer, like the Qualcomm or Renesas or like the customer, they don't have to spend money for that. They will lose the edge that like specific, now it becomes like everybody can use it, but in the other side they don't have to like spend money and manpower on that. So that's what the management like it. The management want like this, one like whatever can be done, it should be done by every employees, not just a couple. If I'm good, I can do it. They want that knowledge to be spread all over the team. They don't want that I know only me know that, because it would depend on me only, right? So if for some reason I quit, then they don't have somebody else to like take care of it. So they will take, sure they will have somebody to like take over, but it will take time. So they don't want to lose those things. So that means like whenever you have a good idea, they want that to be popularized. They want that to be like go in and everybody can use it. And I think if like it need really to be like good, then it's good, then they just transfer that to like the vendor tool. The vendor tool will integrate that into the tool, and they will provide that for the whole company. That's the way they want that to be. So like that means from the employee perspective, we want that's because our like that's our work, right? We have some good idea, we have do that, do this, we want to keep to us. But no, for the interest of the benefit of the company, the management don't want it. So so finally, I think that's why it's like for whatever we do in the PD, the thing we do this is usually we don't have patent for that, because everything we can think or we can like innovate and so on, it will be transferred to the vendor to the tool vendor, so that they can implement that for everybody. So you rarely in the PD world we have the patent. Only in the the RTL like a design, they have the patent, because whatever they design there, that's keep to themselves. They design like a good multiplier, right? Then they keep to themselves, because it will become like a IP block. Nobody see in there. So it does, when they do that, that one can be used by the whole company without like making it like revealing the thing inside. But for the methodology, like when you do the PD, it's very hard to have a patent. Uh, all right, I think piano please. Okay, this from the placement now to the routing. I think this one is not very. I think only that. So I think I will add some more slide in here to explain like how a lot of things here: placement, CTS, routing, and post route. Those things. I think I will add some more slide to explain about this thing. Yeah. Okay, so we stop here. And next time I think will be the last one. And yeah, if you have any question, we can you can ask. So the thing is, yeah, I will discuss with Professor Ten about the format of how to do the final test, and we'll let you know next time. All right. So any question? Oh, okay. There's a question here. So I already asked you, like, if you want to ask something, please speak up, because I just realized. Oh, okay. It's not a question. All right. So if you have any question, you can ask now. It's a little bit. I'm a little bit disappointed that it seems that you guys, all right, not you guys here, because you guys attended the class right now. I think you are interested. I'm just a little bit disappointed that like there's not enough students to who attend the class. Anyway, let's go on. All right. So I think we're done here. Professor, and you have something to add?
Okay, for the student, just next time for the last time for the this course. So please just review all of chapter from chapter 1 to chapter 6, and also some edit document from Dr. Vic. So next time you have the last chance to ask us about this, about the cost, if you have any requirements. Okay, thank you.
Okay. Thank you, everybody. Then yeah, see you next time after the holiday.
Yes.
Mm. Okay. All right. Could you please? I need to talk with Professor Then a little bit for the format. Quốc Anh, Minh, Hải, could you please? Okay, I think just two more. Minh and Hải, are you still there or like it's just
Yes.
maybe we can get to another meeting? We set up another meeting.
Okay, just I will set up another
Yeah,
meeting.
yeah, yeah. Could you set up a new meeting? So you send out another meeting đó
Yes,
ha.
yes, I will.
Yeah, dạ mình quit cái này ha, rồi Thịnh send out sao?
Không, cứ ở đó là em tạo cái
Cái new Google
cái
Meet,
view xong
right?
em đỡ gửi đường link qua luôn mà thầy á thôi.
Yeah, okay, vậy mình quit cái này ha.
Dạ, không thầy cứ ở đó em gửi đường link qua cái chat luôn cho nó dễ thầy.
Oh, okay, all right, yeah,
Dạ,
yeah, okay,
đây em gửi cái đường link cho thầy đó.
yeah, sure. All right, yeah, okay, okay. Let's do join.
Gì bây giờ em thoát cái này thầy.
Giờ mình thoát này ha.
Dạ,
Nó còn hai cái cùng một lúc à?
dạ nó lên bao nhiêu cái cũng được không có vấn đề gì.
Okay. Thoát này xem tại vì thằng kia là nó bằng team á, team là nó